Aloha and welcome to our video on the study of light. In this video, we'll describe the waves that compose the electromagnetic spectrum, we'll describe what different types of spectra reveal about the stars, and finally we'll explain how the Doppler effect is applied to the motion of stars in relation to the Earth. So what we see here is a picture depicting the entire electromagnetic spectrum. We have our short waves down here, our radio waves like our AM, our TV, our FM, the waves used for radar, infrared, which we kind of sometimes mistake as heat, the visible light spectrum, which we see down here, our ultraviolet rays, X-rays, and gamma rays. So we can see an incredible spectrum of waves. We organize them by wavelength. So we'll notice that our gamma waves have 10 to the minus 12 meter wavelengths, versus some of our AM waves are going to have a wavelength that's going to be of about 10 to the fourth. So we can see a huge disparity in the length of the wavelength, and that's what kind of gives us these different properties for each. For visible light, notice that our spectrum is down here from about 400 to about 750 nanometers. Those with the shorter wavelengths are going to be your purples, and our longer wavelengths are going to be our reds. So the entire electromagnetic spectrum is here. What we're most familiar with is going to be our visible light, and then, like I said, some of our radio waves as well. Now, one thing I want to talk to you about when we talk about studying light is this duality, this wave-particle duality that we have. The wave nature of light, okay, is the determining factor for wave motion's ability to produce the interference pattern. So what that means is that if we shine light onto an object, then we can get an interference pattern that makes us suggest that light is actually a wave, these electromagnetic waves. But we also have the photoelectric effect. And that means that electrons being emitted from the surface of a metal given by the incidence of radiation. So if we shine light onto a metal, it knocks off electrons. And because we have that knocking off, then that tells us that we have a particle nature of light as well. So light's really bizarre. We don't know, we can't say it's a definite wave, we can't say it's a definite particle, but what we can say is that it has this duality. It has a little bit of both together. Okay, so let's talk about the formation of spectra. For all of these, what we're going to do is we're going to take some source of light and we're going to shine it through a narrow slit into a prism here, and then we'll see what gets projected outwards. For a continuous spectrum, what we have is our incandescent solid, so a light bulb basically. And what that's going to do is heat that solid up until it starts emitting light. That light is going to transfer through the little slit, like we said, through the prism, and it's going to project a continuous spectrum. So we can see that this solid is emitting light on every wavelength, and that's kind of interesting for us. So if we have this incandescent solid and it emits out that light, it's going to throw out this continuous spectrum. Now, we can do things with this. I can take this solid light that we had before, this incandescent solid, we can shine it like we were, but before we get to our narrow slit, we're going to run it through a cool gas. That cool gas is going to absorb some of this energy, and what we can do is when we run it through and we project up our spectrum, because we're absorbing energy, we have what we call an absorption spectrum. This absorption spectrum is going to show up as that continuous spectrum, but you'll notice that there are wavelengths that are missing, and these are shown by distinct black lines. So that can give us an idea of the nature of the gas that we are shining it through. Different elements are going to absorb different wavelengths of light, and then through this absorption spectrum, it shows me what that gas is made up of. So if we take this to astronomy, if I have a star that's emitting light, as that star is emitting light and goes through a cloud like a nebula, I can see what's in that nebula by looking at this absorption spectrum. Now conversely, if I take a gas and I heat that gas up, that gas, when it heats up, is going to release out energy, or these wavelengths, and then when we run the light from that heated up gas through that slit in the prism, we end up with an emission spectrum. And an emission spectrum is going to give us just these lines. So again, different elements are going to be a little bit different. So by looking at either the absorption, if we have a light source shining through that gas, or if the gas is hot enough to be emitting light on its own, let's say a star, what it gives us is the ability to look at this emission spectrum and see what elements are being represented there. Now, one of the interesting things that we notice with light is it does behave like a wave. So we've heard of the Doppler effect before, and the Doppler effect says that if I have sound and the sound is being emitted by a moving source, and I have two observers, so our sound is the siren on the ambulance and it's moving, we have two different observers or the same observer in different locations relative to the source. Prior to the source, prior to the ambulance coming, it's going to be a higher frequency. And the reason for that is as it's emitting out the sound waves, they seem to be getting squished together. So our frequency goes up, it's a higher pitched sound. Once that source travels by, it's going to be emitting out the same waves, but they kind of get stretched out a little bit, so it'll be a lower frequency. So that's why you notice as a car is passing you, it'll kind of build up to a higher frequency, a higher pitch, you'll hear it going, and then passes you, it goes like that. And that's this Doppler effect. Now, Sir Edwin Hubble was looking at stars and he realized that these stars that he was looking for had a shift in their visible spectrum to the red. And what that did is that meant that the wavelengths were getting a little bit longer. We knew what the stars were made of, we knew what they were burning, but when we looked at them, the absorption was a little bit off, and we call this the red shift. And the net result of this was that by looking at these stars and seeing a shift to the red, that would mean that these stars are moving away from us. So it gave us an idea of where the stars were going. So we could look at a star, if it was shifted towards the blue, the frequency was getting bigger, they would be coming towards us and we'd be worried about a collision. If we see the stars moving away from us, then that would mean we're moving further apart. And by noticing this throughout the universe and what we could see, we noticed that there's just a lot more of this red shift. And the only way to explain that would say that the universe was expanding. But we'll talk about that a little bit later on in this unit. Okay, that's it for our video. As always, good luck on the quiz, and we'll see you in the next video.